Last week I made the mistake of clicking on this video and proceeded to lose my mind trying to solve the problem within it. This is a problem they present in that video and it's ridiculously hard. I eventually did manage to solve it, which I'm pretty proud of, so in this video I'm going to walk you through my proof of this particular problem, the legendary question 6. If you'd like to give this problem a go, pause the video now, but be warned, it is a really hard problem. And also, if you're not one of the 3 million people that have watched the original number file video, go and check that out as well. He does give a couple of hints as how you can start this off. Okay, here are the tools I used in my proof, the quadratic formula and proof by contradiction. Let's get into it. So here we have the famous question 6 from the International Mathematics Olympiad paper from 1988. I'm going to do my best to walk you through this proof, although there may be some parts that are still a bit rough around the edges. So here we have the expression, and they say show that it is the square of an integer. Basically this means when this is an integer, it must be a square, a perfect square. And I'm going to rewrite this in terms of x and y because I just find that more natural. So we have x squared plus y squared over x y plus 1, and I'm going to say this equals some integer n. All right. Now there are many places you can start with this problem. You can start by plugging in values and seeing what you get. You can start by rearranging this equation, and eventually you need to find that you can rearrange this in terms of a quadratic. So if you multiply on the right hand side by x y plus 1, you get x squared plus y squared equal to n multiplied by xy is nxy, n multiplied by 1 is plus n. And then bring everything over to the left hand side so that it is all equal to 0. So we'll have x squared take nyx. I'm going to write it like this. You'll see why in a minute. And then we have a plus y squared take n, and all of this is equal to 0. Now this is actually in the form of a traditional quadratic equation in terms of x. Remember what a quadratic equation looks like. It is ax squared plus bx plus c equals 0. So here we have the x squared term, here we have the x term, and we have a coefficient of x, which is negative ny. Okay, that's our b in this quadratic equation. And our constant on the end is y squared take n. Now this is part of what makes this problem so difficult. This is a traditional mathematical proof in that we don't actually have numbers in here. We have letters, essentially y and n, and what we're going to say is they are now some positive constants. This is where the algebraic understanding really comes in. You need to be able to differentiate between a letter or an unknown that you say is a constant and an unknown that you are looking for the values of. So we are saying now that n and y are now positive integer constants from here on in. Okay, constants in quotes because we don't actually know what they are, but we're just setting the value of them. Essentially we're saying y now equals something and n now equals something such that they are positive integer constants from here on in the proof. So n equals something, y equals something, and there's conditions on those, on what they can be. So with this quadratic equation, we are solving for x. And how would we do this? Well, usually we'd try to factorize. In this case, obviously we can't factorize. We don't know actually what these are. So we're going to use the quadratic formula. Remember the quadratic formula says x equals negative b plus or minus the square root of b squared, take 4ac, all over 2a. And here's something else you need to know about quadratics. For solving for x, you can either have no solutions, no real solutions. You can have one solution, and we're only talking about real numbers here, so this is all that we need to worry about. No solutions, one solution, or two solutions. One solution, sorry about the grammar there. One solution or two solutions. Okay, and what we're going to show is that, well, we don't actually care if it has no solutions. If we say x has no solutions for this quadratic, that's not applicable to our proof, right? We'd just say, okay, well, there's no possible way that x can be an integer then. So we're not really worrying about this situation. We're going to look at these two situations here. One solution, if x has one solution, or if it has two solutions. So I'm actually going to show that this x value must have two solutions for this quadratic. I'm not 100% sure if this is necessary, but I'm going to show that it must have two solutions anyway, and then I'll proceed with the proof from there. Okay, so firstly, let's write this using the quadratic formula and find the two values of x. Let's say x equals negative b. So b, remember, is this negative ny. So negative ny will just be ny plus or minus the square root of b squared ny squared. Take 4 times a here is just 1, right, the coefficient of x squared, and c is this y squared take n. Okay, and then this is all over 2a, but again, a is just 1, so this is divided by 2. And now, what we're going to proceed with here is a proof by contradiction. And if you haven't used proof by contradiction before, there may be steps in here that you don't understand, but I'm hoping that you'll still be able to follow it. Okay, so with a proof by contradiction, what you want to start with is an assumption. And we're actually going to make 3 assumptions in this proof. The first one is assumption number 1 is that n is not a square, a perfect square. And what we're going to show is we end up with a contradiction, so this is going to be wrong. But we'll just leave that to the side for now. That's an assumption. N is not a square number. And let's keep going. So firstly, remember I said I want to show there must be two solutions. So I want to rule out this idea that there's only one solution for x. So if we get one solution, what that means is this term in here, oh, by the way, with a quadratic formula, there's all different parts to it, right? There's this square root part, there's this part out the front, and you're dividing by 2a. I'm just going to focus on this part here. It's called the discriminant, and that essentially tells you whether there's going to be one solution or two solutions. So when there's one solution, this equals 0, right? We don't have this plus or minus. This whole thing is 0. We just get one solution, which is ny over 2. So I want to show this can't equal 0. So I'm going to say that ny all squared take 4 times y squared take n. Well, let's assume that it does equal 0. Again, this is like a mini proof by contradiction within the larger proof. Again, part of what makes this problem so difficult is there's so many different parts to it. But let's assume this is 0. What would we get here? Well, if you rearrange this equation in terms of y squared, let's go ahead and do that. Firstly, I'd expand those brackets. So this is n, actually, let's expand that squared as well. Let's say n squared y squared take 4y squared plus 4n equals 0. And then factorize the y squared, would have y squared n squared take 4 plus 4n equals 0. And then if you rearrange in terms of y squared, you have y squared equal to negative 4n over n squared take 4. And what you end up with is a squared term equal to a negative value. Well, we know that can't be the case. The only way that we could possibly solve this is if n and y equals 0. So unless n equals 0, y equals 0, this has no solutions. This has no solutions. Now, remember the question is talking about positive integers. Now, there can be debate sometimes about whether 0 is a positive integer. We're just going to say we're not including 0 in this proof, right? It essentially cancels everything out. So we're not caring about 0 in this case. Plus 0 is not a square integer. So obviously, this proves there must be two solutions for x here. So we can say, therefore, there must be two integer solutions for x. That's important that they're integers because everything in this quadratic is an integer, so x will have to end up being an integer. Well, actually, no, I haven't proved that yet, but that is coming. So there are two solutions, I should say. That's not actually, I haven't actually proved they must be integers yet. So there are two solutions for x. Okay, so then we're on to the next part. We've shown there can't be one solution, so let's just cross this out. We've said there's two solutions for x. Okay, and here I should point out the second assumption we're going to make. So we're also assuming, actually we could write this up here. There's a second assumption we're making, and this assumption is fine, and I'll explain why. Assumption number 2 is that y is greater than x. Okay, so we have two integers for x and y, or a and b, if you're talking about the question, and one of them is larger. It doesn't really matter which one you say is larger, y or x. It doesn't really matter, because you can still prove it either way. So if you said x is greater than y, this is still going to work out. So this is a valid assumption. And also I should go into a special case here where we have them equal to each other. So this is a special case where x equals y. I could do that down here. So let's assume that x equals y, and you can show that the solutions must be 1. This is a special case. So we would have x squared plus x squared, right, on the top line, because x equals y, and then we'd have x squared plus 1 on the bottom line, and this equals some integer n. Then we'd have 2x squared over x squared plus 1 equals n. And then you can rearrange this in terms of x squared, so you can say 2x squared equals nx squared plus n, and then take that onto the other side. You'd have x squared multiplied by, if you factorize out the x squared from those terms, you get 2 take n equals n, and then x squared equals n over 2 take n. Now, I don't know if all of this is necessary, but this is how I understood it. Now, remember, they have to be positive integers, so the only way this denominator can be positive is if n is 1, right? If n is 2 or greater, this is going to be either 0 or a negative, and if it's 0, it's undefined, so then n equals 1. If n equals 1, x must be 1, and if x is 1, y is 1. So this is the case where they're all equal to 1. This is the only occurrence where this happens. Where any of them are equal to 1 is when x equals y. So that's kind of a special case. So actually, by that, we've proven that x and y are greater than 1, so 2 or greater. And also we're saying, remember, that y is greater than x. So anyways, I'm not sure if all of that is completely necessary, but I'm trying to be thorough here. So, right, let's get back into the actual proof. We've proven there are two solutions. We've made two assumptions so far. One, that n is not a square, and 2, y is greater than x. Let's continue now. Our two solutions. Let's move this over a little bit. Our two solutions for x. Two solutions are, well, that's the negative square root. So we can say x1 equals ny subtract this square root, which was ny squared, take 4 times y squared, take n, over 2. And our other solution is, we'll call x2. This is equal to ny plus the square root of ny all squared, take 4, y squared, take n, over 2. Okay, this is getting in the way now. Sorry about this. You can see this is really getting quite convoluted. Again, this is kind of what makes this problem so difficult. So now what we want to do is make a third assumption. So this is going to be the third assumption in this proof. And we're going to say that x2, y, is the smallest integer solution. Let's assume x2, y is the smallest integer solution. And you might say here, well, how can you assume this is the smallest solution? There might be a smaller one. And I'll point out why this is actually a valid assumption at the end as well. Okay, so this then, x1, therefore x1 must be smaller, right, than x2, right? Because this is the negative solution of this quadratic. Okay, so now what we're going to show is this can't be 0 and it can't be less than 0. And I'll point out why that's important as well. So firstly, it cannot equal 0. Why can't this equal 0? Because this square root then would have to equal ny. Okay, how does this square root equal ny? That's if all of this, or sorry, the terms under the square root are equal to ny squared. Okay, so I'll highlight the different sections of this. We have this bit in here, ny squared, and we have this part here, negative 4y squared take n. Okay, how could all of this equal ny squared? That's if this orange part here is equal to 0. How could that be equal to 0? Well, let's write this down. We would say negative 4y squared take n equals 0. How could that equal 0? The only way this can equal 0 is if n equals y squared. But remember our first assumption, n is not a square number. So this can't happen. Okay, so we can say, but n is not a square. Therefore, x1 cannot equal 0. Okay, so that's the first part of this. We're saying this x1 can't equal 0. Next, we're going to show that it cannot be less than 0. Okay, so this cannot be, x1 cannot be less than 0. Okay, this makes a bit more sense. We can say because then x is a negative integer. Oh yeah, that's the other puzzle piece that fits in here. And this is actually the one that actually caused me the most trouble, or the one that I didn't see. So why is x1, if x1 is less than 0, why must it be a negative integer? Well, remember we're assuming x2 is an integer. Now, for a quadratic in this form up here, to have one integer solution, the other solution must also be an integer. Okay, this is something that for some reason didn't click in my mind. So what I'm saying is, if one of these is an integer, the other one must also be an integer. So they must both be integers. And I can briefly explain why this is, mainly because this coefficient of x squared is 1. And if a quadratic has two solutions, you can always factorize it into two brackets. And because that coefficient of x squared is 1, the first terms in these brackets are x and x. And if one of the other numbers is an integer, the other number must be an integer, because the sum in here, ny, is also an integer. This is kind of why this kind of slipped my mind, or I didn't pick this up, because there's so many parts to this, right? You need to look at this, ny, and say that's an integer, therefore both of these solutions are integers. Let's say this was a half. You know, I don't know what these would be. This is just a random quadratic. But let's expand this out. We'd have x squared. The sum in the middle is 4 take a half, which is 3.5 x. And then on the end, we have a half times 4 is -2. So while the final term could be an integer, this sum in the middle can never be an integer unless they are both integer solutions. And if all of this is getting really confusing, I'm going to go through the geometric sort of understanding of this towards the end. So if you are getting confused, hopefully the ending will make more sense as well. Okay, so because the positive x value is an integer, the smaller x value, x1, must be an integer as well. But it can't be a negative integer. Why? Because let's consider the original equation. Let's consider the original equation. And let's say, and consider x squared plus y squared over xy plus 1 equals n. This would be negative if x1 is a negative integer. So therefore, x cannot be a negative integer if y and n are positive integers. And just to be really clear here, let's just say, for example, x is -1. What would we get down here? Well, remember we proved that y can't be 1. So we would have -1 times 2. -1 times 2 is -2 plus 1. That's -1. It doesn't matter what this numerator is. By the way, it has to be positive because they're both squared. So we would have a positive divided by a negative term. This must be negative, okay? But remember, n must be positive. So x cannot be a negative integer. Okay, all right, so now we've shown that x1 cannot equal 0. I should have written x1 there. x1 cannot equal 0. x1 cannot be less than 0. And we're just about at the finishing line here. Therefore, x1 is a positive integer, so such that x1 is less than x2. And this is a contradiction. This is a contradiction. Okay. And I just want to point out again why this third assumption is fine. So I'm going to underline that. So we assumed x2 was the smallest positive x integer that satisfies this equation. And you might say, okay, but I've just shown x1 is smaller. The thing is, the problem with that is there is a smallest integer, right? What's the smallest integer? It's 1. So eventually you're going to get down to the smallest integer and you're going to let that be x2. But the thing is, you can show then that there is still a smaller integer. But there isn't a smaller integer than 1. Okay, so I think you get the point. You can actually repeat this process. Even if you don't believe this assumption is valid, you can repeat this process and show that it actually is a valid assumption to make. So then you end up with this contradiction. Okay, x1 is less than the smallest possible solution for x. This is a contradiction. And I'm just going to make that note just to make it really clear that there is a smallest integer. So eventually you get down to that smallest integer. You say, well, there's still a small integer. No, there's not. That's a contradiction. So let's say that x1 cannot be a smaller positive integer. Therefore, one of our assumptions is wrong. Let's revisit the assumptions again. I've already just explained why that assumption is valid. The other assumption we made was y is greater than x. That's fine as well. Firstly, we showed they're not equal. And as I explained at the start, you can reverse this. You can say, well, what if x is greater than y? And that would be fine too. And you could show this process as well. So this assumption is fine. This assumption is valid. The only other assumption we made was n is not a square. So this then must be wrong. Okay, so we can say therefore then, assumption 1, assumption number 1 is wrong. It must be a square number. It must be a square number and x1 equals 0. Okay, we got there in the end. That is the full proof of this problem. Now, I want to go through a bit more understanding and the geometric understanding of this. So what this says is actually the smallest integer solution, or the solution below x2 is actually when x equals 0. And let's have a look at the graph of this equation. Let's have a look at the graph of this one here, x squared plus y squared over xy plus 1 equals n. Okay, so this is what the graph looks like. And here I have a slider for n. So we've got different solutions for n, and you can actually see what happens to this graph as n increases. It kind of widens out like that. And if you get lower, it actually collapses in on itself. Oh, I haven't made the thing. Let's make it -10. See what happens. So it collapses in on itself into an ellipse, and then goes the other way. So anyways, let's look at this graph n equals 4, and let's zoom in on the on this section here. So what we said in our proof was we assumed this value here for x, 8, 2, this point here. We said this is the smallest integer solution, and we wanted to look for the smaller integer solution. And we said, well, if n is not a square number, okay, x0 it won't be an integer solution. Actually, let's make this something else. Let's make it 6. And you can see here the graph now cuts at a number that's not an integer. So we said, well, assume this is the case. Assume this is the case and there's some integer coordinate out here. And then we said there must be a pair. There must be an x value paired with that solution over here, this coordinate over here. So what we were doing in terms of this graph is saying we're coming over here now and looking for an x coordinate with the same y coordinate. So let's say it was at 3 or whatever. 14, 3, I don't know, 15, 3, something like that. Actually, what would it be? About 18, 3. And we're coming over here and saying, well, okay, it can't be on the y-axis. There can be no point on the y-axis because n is not a square number. And it cannot be below. It cannot be in the negative x values. And let's just have a look at this point here. This point here at -1, 1. You can see the graph just dips below that point. So there is no positive y value where there is a negative x integer. Okay, so it never crosses this point here at -1, 1. So it just dips below that. The y integers or the y values are less than 1 for every x, negative x integer. So we said it cannot be where x is a negative integer. It cannot be 0, so it must be up here somewhere. And the problem with that is eventually you get to the lowest value and you can't keep going. You have to eventually cross this y-axis. You have to get into the negative somehow. The only way that can happen if we're talking about integer coordinates is if we actually hit the, what's going on? 4. I want 4. Okay. If we actually hit the y-axis at the y-intercept. So we come across from 8, 2, hit it at 0, 2, and then go down again to -2, 0, -2. They're the pairs, if you like, pairs of solutions. So that's kind of essentially, to me, that's what the proof kind of hinges around, the fact that this graph never goes above this point here at -1, 1. And you can see even if you increase this to 50, it approaches that point, but never does. And we showed that algebraically as well, because then you would have a negative n. And well, if it does go negative, then you do get that situation. But for all positive n's, it never actually goes past that point, unless n equals 1, of course. Okay. All right, so that was my solution to this problem. I want it on 4 again. Actually, let's go to 9. Why not? Okay. And you can see that crosses at 0, 3. All right, so that was my proof for that famous question 6 from the International Mathematics Olympiad 1988. Now, I've actually created a flowchart of this proof, of the steps we took, because all of this is, I think, quite confusing, but it does simplify down to this process. So this is the proof flowchart, if you like. Firstly, we arrange the equation as a quadratic in terms of x, or a, if you're talking about the original question. We showed that it must have 2 solutions for every positive integer y, or b. Then we proved that the smaller x value cannot equal 0 or be less than 0 if n is not a perfect square. Therefore, we could say n must be a perfect square, as there is eventually a smallest integer. Okay, so that is the general flow of that proof, or the steps, the logical steps I took. I hope you found that useful. I'm tried to make that as clear as possible. There are many other proofs of this problem, as I said, because it is quite a well-known problem. That number file video, of course, has something like 2 million views, so there's a lot of people that have seen this problem, had a go at it. If you didn't find this proof particularly logical or it didn't quite click for you, check out the many other proofs online of this question. Thanks for watching. I'll see you in the next one. Bye for now.